Right, okay, hello, and welcome to, well, this is actually a combination of part 2 and 3 of our Key Stage 4 look at energy. So this is a continuation of our original series of 6 lessons for Key Stage 3. In the first lesson of Key Stage 4 of energy, we were looking at the 10 different energy types. So hopefully by now you've got drummed into your head that most kids hate learning the GCSE energy names. If not, you should have learnt that by now, because we're going to be moving on to slightly different subjects now. We're going to be looking at heat transfer, and we're also going to be looking at thermal radiation. Now, both of these topics were Key Stage 3 topics, so you should have the foundations there of what we're going to be looking at. I will be making some references back to Key Stage 3, so don't worry, but if you don't really understand anything about it, have a look back at Key Stage 3, then come back here, and we should be able to, between those 2 lessons, everything should be sorted out for you. Okay, so let's have a start then. So, as we said back in Key Stage 3, there is 3 main types of heat transfer. There is conduction, convection, and thermal radiation. So, conduction. As we explained before, conduction is obviously to do predominantly with solids. It does happen in gases and liquids, but they're not very good at it. So majority of the time it happens in solid materials. The best types of conductors, as we explained back in Key Stage 3, are metals. Now this is because basically the way that conduction works, again as we explained in Key Stage 3, is the vibration of atoms within these materials. So let's sort of have a little chat about exactly what is going on there. Now the way we explained it before is that the atoms are just shaking and bumping into each other. Now this bumping and collision is obviously what causes the thermal energy that's being excited from this heat source to be passed along to the atoms. Now that's not entirely 100% accurate. What is actually happening here, if you imagine what we've got here is our atom. Now as we know, our atom is made up of a nucleus in the middle with surrounding electrons around. Now in any piece of metal, what you actually have in a solid piece of metal is that the outer electrons of those atoms can pass freely in between the atoms. Now when you add a heat source, certain amounts of those atoms start to vibrate more, and now those actually move on to the electrons, and those electrons move faster, and it's actually those electrons that actually move in between the atoms. Now as that electron moves, what actually happens as it detracts itself apart from its atom that it's come from, that atom becomes something called an ion. Now that electron, as I said, travels in between the atoms. Obviously the hotter it is, the faster it's going to travel. Now as we explained before, the faster it's going to travel and the more of them travelling means there's going to be a greater chance of them colliding into each other. Now it's this collision that actually causes the energy itself to be transferred across from one electron to an ion, and then that ion's energy is then increased, so then the electron that's associated with that atom is freed away and carries on, so forth. So that means that from our hot energy source here, through conduction, is actually spread across to the cooler parts of the material that it's made from. As I said, in this case it's made from metal. So as we explained at Key Stage 3, it's the atoms that's shaking, but when you get to this Key Stage 4 level, we need to get the idea across is that actually with each atom has these surrounding electrons, and these electrons are not necessarily shared, but they can transfer in between the atoms along that piece of metal. And the more heat that it's given, so the more energy, the more thermal energy that it's given, the faster it moves. And it's not just that one that moves, it's all of the ones around them are moving, and they're moving faster, and there's more of them moving. So there's more collision, so therefore the heat transfer starts to spread out across the piece, across the material that it's actually made from. So that's conduction, that's our next step on there. So remember, it's all about the electrons moving in between, causing our ions, colliding with those ions, transferring that thermal energy, and that just happening millions and millions of times as it spreads across and causes conduction across our better conductors, which are obviously metals, as we described before. So that's conduction. So convection. Now, as we explained, convection generally happens in gases and in liquids. It doesn't happen in solid. Now, as we explained in key stage 3, convection is where a molecule is heated and it rises, and as it cools, it falls back down again. So, what actually happens here is as the molecules, very similar to conduction with the electrons, as the molecules are heated up, they get more excited, so they start flying around quicker. So what actually happens is that they become, on a whole, less denser. Now, the actual molecules themselves do not change shape. The molecules do not change size, they stay exactly the same. All that happens is that they are given this injection of thermal energy, which makes them just causes them to go faster, move faster. So that actually means that the gas or the liquid itself actually expands because they're moving faster, and all of them are moving faster. They're wanting to go to different places more often. So therefore, there's a greater space in between all of them. So overall, the gas or the liquid itself becomes much larger. And that's what we call expansion. Now, as that energy, that thermal energy in the individual molecules starts to dissipate away to the atmosphere, to its surroundings, it starts to cool down, so therefore the molecule itself starts to slow down. This means it's travelling less time, it's travelling less distance, so therefore the molecules are coming closer back together again. And this means that they become more dense, or they become denser. And this means that they become technically heavier, so therefore they cool and they start to fall back down again. So as we said, a greater volume, so that as soon as they have more thermal energy, they're going to be moving faster. So actually they're going to take up a greater volume, they're going to expand out. Remember, it's not the molecules that are changing size or shape. The molecules themselves stay exactly the same. They just have more energy, which means they want to travel faster, they do travel faster, and they want to travel greater distances. So that greater distance means it expands, it has a greater volume, which therefore means we have a lower density, or it has less density, because there is less of those molecules in the same place when they're hot because they're travelling around all over the place, than when they're cold because they're slower and they don't have the energy to get there. So they'll be smaller, so the colder an object is, the colder the gas or the liquid is, the denser it will be, then the hotter it is, because, as I said, those molecules are moving slower, they have less energy to travel those distances, so there'll be more of them in that one space. Okay, so that was our more extensive look at convection. So what we're going to do now is we're going to have a look at thermal radiation. Now, this was something that was brought up at Key Stage 3, but it was only very briefly mentioned, and really the main way that we talked about it was one of how heat and light radiation, or in this case thermal radiation, comes from the sun, and also the fact that any object itself can emit thermal radiation. It just has to be, the hotter the object, the greater thermal energy that that object has, the greater thermal radiation it will actually emit. Now, as we said previously, thermal radiation is also known as infrared radiation. Now, what is infrared radiation? Now, as you can see that this gentleman here with his glasses on, and these are just normal glasses, they're not sunglasses, you can see that the sun itself emits massive, massive, massive amounts of thermal radiation. But even the human body emits thermal radiation. Now, this actually is a very good look at how insulators work. We were looking previously at conductors, or conduction, and we said in Key Stage 3 about anything that doesn't conduct thermal energy well is a good insulator. So we can actually see here that this gentleman's wearing a shirt. Now, when the shirt itself is actually touching the body, you can see that this heat, the brighter the colour, the hotter it is. When it's actually touching the body, then the material itself is actually quite hot. But where the material is not touching the body and there's air in between, it's relatively quite cold. So what this actually shows is that materials themselves are actually not very good insulators. But when there is air in between the material and your body, it's the air itself that actually works as quite a good insulator. But anyway, I get completely off the point because we're talking about thermal radiation. So we were saying about infrared radiation. So what is infrared radiation? Basically what it is part of something which is called the electromagnetic spectrum. So what's this? Okay, so the electromagnetic spectrum. This is the introduction to waves. As we said, there's sound waves, which is to do with vibrations. These types of particular waves that we're talking about here, though, as I said, is from the electromagnetic spectrum. So, first of all, if we think about just like a beam of light, if you actually put this through, what this object is called a prism. It's basically just a prism shaped, as the name suggests. It's a triangle where the light actually passes through the prism itself. As you can see here, we have several different colours that come out. Now these different colours are all different wavelengths. Okay, so the longer the wavelength, a longer wavelength will be a different colour to a shorter wavelength. Okay, so let's try and actually explain this a little bit better. So us ourselves, while visible light, we can only actually see a very, very, very small section of this electromagnetic spectrum. But the rest of the spectrum are still very, very useful to us. So at the shorter wavelengths, so the high frequency, so there's lots and lots of waves in a very short space of time. Okay, so there's lots and lots of them. These are called gamma radiations. Now these are really, really quite harmful. But they are actually good for treatment of cancer. Then you go down, we have X-rays, which again are high frequency, not as high frequency as the gamma rays, and a little bit longer wavelength than gamma rays. And X-rays, if you've ever been to hospital, if you've ever broken something, or really injured yourself, then you have an X-ray. It's a really funky way of looking at the inside of your body, really quite peculiar. Then there's ultraviolets, which are still above this visible light. If you've ever been to Laser Quest or anything like that, it's like blue-purple lights. You can see all the little white bits of white flick on your t-shirt. Or if you wear white, it starts to go really, really bright. Then we actually have our visible light, which is sort of really quite in the middle of the frequency and wavelength range. Okay. Now, as I said, this is just actually the only bit of the light that we can generally see. And it's not just the higher frequency, shorter wavelengths that we can't see. There's actually ones with lower frequency and longer wavelengths that we can't see as well. This is where infrared comes in. So now infrared is not just wavelengths that come from the sun that carries the thermal energy from the sun, but infrared is using optical fibre. It's how a lot of people, you get your broadband and you get your digital TV. It's from optical fibres. There's this infrared light transmitting data through these pipes. Infrared it's how your TV remote works. So you can't actually see infrared, but it's really, really useful just on a daily basis. And as we go into the lower frequencies and longer wavelengths now, then we're looking at microwaves, so everything you chuck in the microwave, that's using a really sort of low frequency, low wavelength. And also the lowest one that we have, well just on here anyway, is radio waves. So every time you listen to Radio 1 or whatever radio station you're into, this is all the lower frequency and lower wavelength. So that's our brief introduction to electromagnetic spectrum. So back to thermal radiation, trying to get back onto the point. There are different materials that actually emit and absorb this thermal radiation better than others. Now, what we have here is obviously different colours. The darker the material, the better it is at emitting thermal radiation, but also the better it is at absorbing thermal radiation. So you see, I'm wearing a black t-shirt, so if I went outside in the sun and my mate stood there with a white t-shirt, my t-shirt would be warmer than his white one, because my black t-shirt is better at absorbing thermal radiation from the sun than his white one would be. His white one would be reflecting more of this radiation back. Because it's thermal radiation, because it's a wave based, it can be rebounded. That's why when you talk, you're talking and sound is a wave. That's why in like this very bare walled room, you can hear my voice echoing. It's because waves can bounce off objects. So as I said, the darker the material, the more thermal energy that it can absorb. But also, it's better at emitting it. So, in theory, radiators, okay? Radiators generally speaking, are white and shiny. Now, because they're actually an energy source, the energy itself is coming from inside it. And there's actually a reason why radiators are that shape as well, because the bigger and thinner the object is, the better it is at emitting thermal radiation than if it was much smaller and fatter. That's generally just because of area. The surface area that a thinner or wider, thinner object produces is much greater than a smaller, fatter one. But going back to what colour they are, they're white and they're shiny. So actually, in theory, the heat being radiated out from a radiator would be hitting that shiny paint. But if you think this is the inside of the radiator behind my hand, so what we want to do is have the heat radiating out through my hand. But this is a shiny surface. It's not just shiny on the top, but it's shiny on the inside as well. So actually that heat radiation is hitting that shiny bit on the inside and rebounding back into the radiator. So why don't more radiators look like that? Why are they not black? And why are they not matte? You know, why are they not shiny? That would mean that more heat would actually radiate straight through the radiator and not rebounding off these shiny surfaces. This actually means, because they're white and shiny, the majority of the heat actually comes out of your radiator and warms your room up is actually done by convection, not actually by thermal radiation. Yeah, not entirely sure why radiators are white and shiny. They should be black and matte. I think I'm going to go and paint mine when I get home. So, that was our look at heat transfer and thermal radiation. So a quick overview. We've had a more in-depth understanding of conduction, convection and thermal radiation. At least I've tried to explain it in a more in-depth way. I hope it's actually come across that way. We had a really brief introduction to the electromagnetic spectrum. That itself is actually a really big topic. If that's confused you a little bit, there are some really good sources online to have a little bit more of a read up about that. And also we had, just at the end there, a look at thermal emitting and absorbing materials, how their different shapes and their different properties make them better or worse at either of those. Okay, so that's the end. Our next lesson is going to be looking at reducing heat loss, both from a person and from your house. And we're also going to be looking at having another look back at energy transfer diagrams and efficiency of energy uses. Okay, that's the end of the combination of lesson 2 and 3. Cheers, thank you.